All right, students, I got a great question on number 20 or 26, number 10, and this one is one involving a moving particle in a well, it's a uniform field because it's between two parallel plates. Let me just read it here. It says a 10 microfarad capacitor has plates with a vacuum between them. Each plate carries a charge of 1,000 microcoulombs. Let's go to the top here. A particle with a charge of a -3 microcoulombs and a mass of 2 × 10⁻⁶ kilograms is fired from the positive plate towards the negative plate with an initial speed of 2 × 10⁻⁶. Does the particle reach the negative plate? Explain how you can tell. If it does, what is its impact speed? If it does not, what fraction of the way does it make it? Okay, so what we need to understand first conceptually is that we have two plates, and normally I put my plates parallel horizontally. I'm going to switch that up here for this problem. Hopefully you'll see why. I hope it'll help you better understand this problem. But I'm going to put a top plate that is horizontal, not vertical. So the plates aren't like this. The plates are like this. And I'm going to put the bottom plate, again, the same way. They have to be. They're parallel plates. So, again, I could have drawn them like this, or I could draw them, like this. And I'm going to draw them like this purposely because if I make this bottom one positive and the top one negative, and you say that down here at the positive plate, I shoot up a charge of Q. And that charge Q, remember, is negative. They said it's -3 microcoulombs. Your thought should be saying, well, Wayne, it doesn't want to go there. This plate is negative. It would push it away. And this plate down here is positive. It would want to attract it back. Yes, exactly. And so in order for it to go up at any particular distance, we've got to give it an initial velocity. And so it does give it a speed of 2 million meters per second. And the reason I decided to draw them this way is I hope you see the analogy of what you would have done last semester. Last semester, or 2 semesters, back in Physics 121, if you had the Earth and you had some kind of object, so let's make a little baseball here, and you throw the baseball upward, clearly the baseball is being pulled down by gravity. It doesn't want to go up, but it will. It'll go up for a while, and eventually it will stop. Unless it's going really fast, then it'll escape. But let's hold off on that. But just throwing a baseball up, it'll go up until it runs out of kinetic energy, because it's really given all of its kinetic energy to potential energy. It comes to a stop, and then it falls back down. And so how high does it go? It doesn't really want to go up. And that's what this one does. It doesn't really want to go to that other plate. But how high it actually goes depends upon that initial speed. And so something with a small speed barely goes up. Something with a bigger speed goes even higher. And the more initial speed you give it, the higher it gives. And you can use energy to figure that out. And so I'm trying to say the same thing here. And so I'm trying to say, do you see the same kinematics that you did in Physics 121 that you have here? The only difference is in 121, this was the force of gravity. Here it's an electrical force. Or maybe I should say here it is gravitational potential energy, and here it'll be electrical potential energy. Okay, but other than that, it's really the same type of problem. So if you thought of maybe the ceiling up here, you could say, will it hit the ceiling? Do I give it enough speed? And that was the question. Is this speed of 2 million meters per second enough for it to get to the top? Is this enough speed to get to the ceiling? And the question says, if so, then, state yes, and then also say what speed does it still have when it gets there. It says, does the particle reach the negative plate? Explain how you can tell. If it does, what is its impact speed? But if it does not, what fraction of the way did it make it up? So maybe, it would only go halfway up or 3/4 of the way up before it comes to a stop and turns down. So I think a big part of this problem might be the beginning, conceptual, just making sure you understand the kinematics. And so you have to take the new stuff we've been learning with potential and then change it over here to the idea of the kinematics. And so we need to put Physics 121 together with our Physics 122. Okay. So maybe I'll just answer the beginning part of this, and that is about energy. See, the energy says that the energy you start with is equal to the energy you end with. So like we would be doing here on throwing a baseball up, we would say it would have some initial kinetic energy and some initial potential energy. And then up near the top, it would have some final kinetic energy, and it would also have some final potential energy. Okay. If we kind of rearrange this and put initial over to here, we would have then final potential minus initial, so that would be the change in potential. Over here, we would just have initial kinetic minus final. And so this would be the change in potential energy. Okay. Now, we know this. And this is how we're going to answer that question. Does it actually make it? The lowest the final can get is 0. So let's say, what is the maximum kinetic energy we could lose? It would be 1/2 mv initial squared minus 0. That's the most that we could lose. That is the loss of when it gets to its maximum and it comes back down. Okay? So maybe what we should do is see what that max is, but then also see what is the change in potential as it moves from, I'll call this the floor to the ceiling, so it follows the analogy of the Earth here, from the floor to the ceiling. So maybe I'll do the floor to the ceiling first. How much energy would it take? And that's where I guess this would be the last chapter, chapter 25, comes into play here. Okay. Here's where chapter 26 comes into play. Maybe I'll put it up here at the top. Remember, capacitance is the charge per volt. Okay. Now, if you read this problem, you'll see that they've set it up more for this chapter than last chapter because they give us its capacitance. So a 10 microfarad capacitor with a plate in a vacuum. Each plate carries a charge of, and they give us the charge. And so they are essentially telling us what the voltage difference is between them. So here's the charge. The potential voltage difference would be the charge we put on the plate divided by its capacitance. All right, so this charge that's moving from the floor to the ceiling, okay, would be and I guess we can debate here if I should put a negative. Part of me wants to put a negative here. But I need to be careful with this because this formula here, if I just go magnitude of charge over magnitude of capacitance, gives me the magnitude. But as it goes up, this is actually a decrease in potential. So technically this change in potential from here to here is a negative, and the charge is also negative. So both of these are negative. So maybe I'll put then the charge is a negative, what I read, 3 microcoulombs. And the change in potential is a negative, and I got to get that from my picture because I'm going from a positive plate to a negative plate. And its value is given by the absolute value of the charge on the plate divided by its capacitance. So the absolute value of the charge on the plate is 1,000 microcoulombs. And the capacitance is 10 microfarads. Now maybe for a farad, I'll put coulomb per volt. Because then coulombs would cancel with coulombs and you'd be left with volt. And a volt, remember, is a joule per coulomb. So if I call this at the top, joule per coulomb, then that coulomb would cancel with that coulomb, and you would be left with energy in joules. Okay, so this gives me the idea of how much energy it's going to take for this charge, this 3 microcoulombs, to get to the top. Okay, so this would be, and let me just get rid of that negative and that negative. So this is 3 times 10 to the negative 6 times 1,000 micros divided by 10 micro. I guess I could have canceled out the micros and saved me some keyboard work. But it looks like 3 times 10 to the minus 4. So 3 times 10 to the minus 4. Oh yeah, these are all powers of 10. I guess I didn't need a calculator for that. But that would be the, is that right? 1,002. Yeah, okay. That would be how much energy it's going to need to go from here to here. That's, like I said, the chapter 25 together with the chapter 26. How much energy does it take to get up there? Okay, now let me go ahead and come over here and see, does it even have that much kinetic energy to give it? Because I'll say it again, if it doesn't even have that much kinetic energy, it can never get to the ceiling. Okay, it would never get to the top. So let's see what this number comes out to be. So we've got 1/2 times the mass of the particle, mass, 2 times 10 to the negative 16th, times its velocity, which is 2 million meters per second, and so I will square that. And just check my units. Let's see, I did mass in kilograms and speed in meters per second, so this is going to be in joules. And so this kinetic energy is 4 times 10 to the minus 4 joules. Which is greater than what it needs. And so it has more than enough energy to get to the ceiling. And if it would go even further up. So this first part of it, it says, does the particle reach the plate? The answer is yes. How do we know? Well, we know because we have enough kinetic energy to overcome the need of the potential energy, in this case electrical potential energy, as opposed to gravitational potential energy if it was a Physics 121 problem. But we have more than enough energy now to get to the top. All right. So now it says, if it does, what is its impact speed? And if it does not, well, I'll leave that at that. We don't have to answer that one if it does not, because we know it does now. All right, so now I can come back here and say, all right, the initial kinetic minus the final kinetic would equal the change in energy. All right, so let's imagine it goes all the way up to the top. As we just calculated, the negative charge with a negative change in potential would be an increase of positive energy of 3 times 10 to the minus 4 joules. Okay, so that's how much it gains in potential energy. So that means it must lose kinetic energy. Its initial kinetic energy, which we just calculated as 4 times 10 to the minus 4 joules, minus the final. So if we rearrange this, we could bring this over to here and get 1 times 10 to the minus 4 joules for the final kinetic energy. So in other words, we have 4 times 10 to the minus 4 joules down at the bottom. And as it goes up, we have to gain this much potential energy, so we lose that much potential energy. So we're only left with 1 times 10 to the minus 4 joules by the time it gets to the plate. So I'll say it again. Yes, it gets to the plate. Yes, it's still moving. But now we can figure out how fast it's going, because this could be 1/2 times mv final squared. And so now we can grab our calculator and say, all right, let's take 1 times 10 to the negative 4, multiply it by 2 when we bring that over, divide by the mass, which is 2 times 10 to the negative 16. I'll just hit enter, so that would be the speed squared. And the square root would be then 1 million. 1, 2, 3, 4, 5, 6. So 1 times 10 to the 6th meters per second would be its speed. So starting with 2 million meters per second, it would end up slowing down and be going only 1 meter per second by the time it gets to the top. So hope that helped. Maybe just as a recap, I want you to notice something here. Did you notice this was the only thing I used in chapter 26? So that's the new piece. But we did a lot of old stuff. We did the energy from chapter 25. We did the conservation of energy way back to chapter 8 in order to figure our kinematics out, to figure out how fast it was going when it got that high. So never forget your old stuff. You need that as things build up. All right. Hopefully that helped.